Okay, everyone. I think we're going to get started. First of all, Dr. Ethier is still out sick. As most of you know, he wasn't in the flip session on Friday, and he contacted me this morning that he's still really under the weather. So I'm filling in very last minute, so I apologize if this is a little bumpy. I also haven't had much communication with him, so I'm a little unclear as to where you guys left off. I know he wanted us to discuss Bernoulli, and I wasn't sure if he got through the derivation of the Euler N and S equations last class. No? Okay, so then you got through the tear film example. Okay, great. So we'll discuss, we'll pick up right here and then move forward. So before we get started, I want to talk a little bit about the MATLAB assignment because there was a lot of activity on Piazza. And some of you have emailed me with questions. Other people have posted similar questions on Piazza. And it's good if you're recognizing that your answers are nonsensical or that they don't fit what you physically know is going on. What I would suggest, the number one thing I'm seeing as far as mistakes in the implementation of the dA/dN expressions is not having your right-hand sides reflect the interdependence of those two equations. Right? So if you have a variable that's just a function of v1 for your first equation, and you have a variable that's just a function of v2 for your second equation, those are going to be integrated separately without any communication between the two. But you know f and g are related to one another. So those right-hand sides have to somehow be interdependent on one another. All right? So I'm going to let you mull that over. I'm not going to be directly answering any, is this right? Or tell me, how to get this right-hand side. That's part of the assignment. So I don't want to give away any more than that. But I think you have all the tips you need at this point to be able to implement that correctly. Okay? Okay, so we're then going to start in on Bernoulli's equations. And I know some of you, depending on your 2210 instructor, have probably seen Bernoulli's before. How many of you have seen Bernoulli's? Yeah, so it is dependent on the 2210 instructor. Okay, so sometimes, depending on who's teaching 2210, they touch upon this from a very, as you've noticed in this class, we're moving from sort of an integral approach to a differential approach to things. And so sometimes you've seen this from more of an algebraic relationship rather than through the derivation of Navier-Stokes and a specific case of Navier-Stokes. So for those of you that have seen Bernoulli's already, you're going to be revisiting this but from a very different perspective. So if we start by considering Navier-Stokes simplified so that we're ignoring fluid viscosity. So what are cases when we'd actually ignore viscosity? Doesn't everything have viscosity associated with it? Well, some fluids are more viscous than others, right? So usually we consider blood to be a lot more viscous than air. Ethanol is going to be a lot less viscous than water. So there are cases where we can make these simplifying assumptions. And sometimes we'll use Bernoulli's for cases when we're ignoring fluid viscosity, but we're doing it in a very, just as a simplified relationship. Dr. Ethier is going to be going into a lot more detail with real fluid flow, where we take into account drag forces and all of these viscous relationships as they play into the properties of fluid flow in the next section. And when you get into that section, you'll have some guidance as to when you can ignore viscosity and when you can't. So that's kind of a teaser of what's coming ahead. And for the moment, we're just going to say, okay, let's pretend this is air instead of liquid. And we'll go under the assumption we can ignore viscosity for the moment. So if you do that, then your Navier-Stokes, okay, I'm going to try to do this here. Your Navier-Stokes here is going to be ignoring that viscous relationship. So it simplifies into the substantial derivative times density equaling just that pressure gradient plus your gravitational force. Okay, so already we've simplified something right there. And then we can make some other assumptions, such as the fact that the flow is steady. So then going down here, and that the only body force term is due to gravity, so that we're considering the z component alone, and so this substantial derivative is going to be rewritten on the right-hand side as this. So we've taken our substantial derivative and we've made it into the velocity dot product with the the gradient of velocity here. So that right-hand side then just becomes rho times this expanded form of the substantial derivative. And then we're going to consider just the z component for our gravitational force. And we're still writing this as the pressure. We don't know the directionality of that, so we're leaving that as it is. But you can then rewrite this then as minus times the gradient of your pressure plus rho g z here. So along here, we're going to consider the fact that we've got streamlines. And each streamline has its own velocity component to it. So we first saw this in Friday's flip session class when we were talking about how basically you can consider each point in that vertical direction as having its own velocity vector associated with it. So you couldn't just multiply v times t there. You had to consider the integral of that. And if you consider those streamlines, so you let a particle go and it's going to follow a trajectory, and you put a particle somewhere else, it's going to follow another trajectory. And those are completely predictable, but they're going to have different properties associated with them. So if we consider that they have this s coordinate that's going to lie along the streamlines, and it's going to basically let you follow that path that the particle is going to follow. And then you've got an n coordinate that's normal to the streamline. So there's a nice picture of this. Oh, that's not good, is it? Sorry, I'm getting used to this. Let's get rid of that. I don't know how to make it so it doesn't follow me. So if you look at that picture then, we can consider for an arbitrary function that if we've got this streamline in the s-coordinate, and we can say that that's basically arbitrary, but it's going to be following that particle path, and then that n is just going to be that orthogonal vector and the coordinate associated with that. As this particle is moving along, you're going to have this coordinate system that's moving with that particle. Then for some arbitrary function, you can then rewrite your velocity fluid speed as a v df ds. And this allows you to write that simplified Euler equation as dv ds plus your gradient pressure plus your gravitational component equaling 0. So if we substitute in what our velocity represents here, then we've got a relationship in which we've got a coordinate system and a partial derivative with respect to that coordinate system. So instead of thinking about this as d dx, we're thinking about it in terms of a d ds here. And we can write each one of these in terms of that coordinate es and dv ds for substituting in this here. Why are we doing this? We're doing this because this allows us then to describe for any streamline the behavior that's going along this. And we can also do this for the normal direction here. So if we want to consider the curvature of the streamline, the Euler equation then can be rewritten in terms of our n-coordinate, our normal coordinate. And this really becomes useful because then as these streamlines are moving through these fluid fields, we can consider a difference in that particle behavior based on where it is in the curvature of the fluid flow. And this is actually going to become really, really important when we get into the example later on in the class. So if you have something for your normal vector that's dependent on r, then what we're going to see is eventually we're going to arrive at a relationship where you're going to have a pressure difference depending on where you are in that curvature of the streamline. And that in and of itself is going to influence the velocity that follows for a particle depending on where it is in that fluid flow. Okay, so we've got a relationship that can be written in terms of S, and we've got a relationship that is in terms of N, and ultimately we get the Euler N equation and the Euler S equation, then that tells us how P plus rho GZ varies across streamlines, or P plus rho GZ varies within the streamline. Okay, so it's like a longitudinal description versus a lateral description in a way. Okay, so that was all sort of independent reading, but I wanted to kind of get us familiar with this idea of streamlines before we step into how we're going to use these N and S equations. So now if we consider this, let's see here. If we've got our streamline going like this, and we've got another streamline going like this, and we want to consider what's happening at, I'm having a hard time here. This is a 1 versus a 2. Oh, I'm sorry. I've got this the wrong way. Let's do this. We've got a 0.1 and a 0.2 in this direction. Then if we want to consider what's happening along a streamline, remember this is the S direction, then we can integrate the Euler's equation between those two locations and arrive at this Bernoulli's equation, which is considering steady, lossless, incompressible along a streamline. So that's saying we've ignored the viscosity term, that's the lossless. We've ignored the time-dependent component, that's the steady. We've ignored a change in the density, so that was pulling the density out in front so that it was independent. And then we're looking at this along a streamline, which considers that Euler S equation. And then we're essentially looking at 0.1 versus 0.2. So we can look at, if we integrate this from S equals one location to S equals another location, then we'll get this relationship here. So this can be rewritten. And actually, I'm less familiar with the Bernoulli's equation in this way. I usually see it in a form which is more like P1 plus rho GZ1 plus rho V1 squared over 2 equals P2 plus rho GZ2 plus rho V2 squared over 2. And in fact, if you take this further, you could write this as some kind of delta P plus rho G delta Z
plus rho over 2 v1 squared minus v2 squared equals 0.
Okay, so if you think about it this way, then essentially he's rewritten it here as the head or total head of the fluid. What this does is this is like really breaking this down into different energy components. This is saying that the fluid flow has some kind of potential energy associated with it. It has some kinetic energy associated with it. And then it's got this delta P. So a question is, how can pressure be energy? If you think about this, right? This is like a rho GH. This is really
potential. And this is kinetic.
How can you have pressure or change in pressure be an energy term? This is actually something that is kind of a deep question. It's not to be considered lightly. It's something that there have been entire scientific essays written on, and the interpretation of what this means in Bernoulli's equation. It turns out that the best way to think about this is work done by the fluid. Okay, so it's a component that's capturing how that change in pressure is causing work to be done by the fluid itself. And then this is considering the motion of the fluid and that potential energy term from a change in height. Okay, so with this in place, we've got a very specialized version of Navier-Stokes that tells us if we want to follow a streamline, again, a single streamline here where we're looking from point 1 to 2, then we can calculate any of the components within this equation for a particular situation. So if we want to know what the change in height is, if we know things about V1 and V2, we can calculate that. If we want to calculate the starting velocity, because we're measuring something on the other side, and we know a change in pressure, we can calculate that. If we want to know what the change in pressure is, and we're able to say something about the velocity itself, then that's also useful. And we're going to soon see that if we know stuff about the area, the cross-sectional area of fluid flow, that actually provides information on how we can solve for any of these as well. So what I was hoping to do today is there are a number of really great applets online that will let you test all of these properties. And this is basically a nice demonstration of how you can look at different geometries and look at how the fluid flow will change for the different streamlines under these conditions. And it'll plot pressure, flow rate, velocity, all these things for you. I can't override the security settings for Java on this computer, so I can't show it to you. However, I got to this just by doing a Google search on Bernoulli and applet. And the first few ones, there are several of those that I've used in past semesters in which you can pull those up and look at them. It's really nice to play around and try to get a better feel for these relationships between pressure, velocity, and flow rate. So if we've got this, I don't understand why this is not staying put. It's rolling with me. Okay. We'll figure this out eventually. So if we want to then look at how we can apply this with changes in cross-sectional area, we can look at this example here in which you've got blood flowing through an artery. Again, we were talking about conditions in which we can use this incompressible, lossless, steady state solution. Blood flowing through an artery pretty much is far from that. We know blood has viscous properties to it. We know that this is a pulsatile flow, so steady state isn't really going to apply here. Incompressible, yeah, you can consider blood to be incompressible. But for the simplicity of this example, we're going to use this. And then we'll show how at least the viscosity term is more or less okay. So here we've got one side that's at one cross-sectional area. We have another side that's in another cross-sectional area, and we have a pinch point in between. And this is due to stenosis here. So we have atherosclerosis or something going on here. And so then we're going to say, all right, when you have that pulsatile pressure forcing the fluid across that pinch point, can we consider what the arterial pressure is going to be doing downstream? And is that a point at which the artery will actually collapse? So we know that there's going to be a 90% reduction in that cross-sectional area. We've got a pre-stenotic mean blood velocity to consider and a pre-stenotic pressure to consider. So we're going to first use those approximations to say that we can apply Bernoulli's equation here. And we note in the text here that there is going to be significant loss. When I say significant loss, what am I talking about? We're kind of getting ahead of ourselves a little bit with the second unit coming up here. So frictional forces that would actually be strongly decelerating the fluid flow. Okay, so if you think about a pipe and the roughness of that pipe reflecting the speed at which something travels from point 1 to point 2, then that would be considered a loss in the fluid. So here, this is basically saying there are significant sort of deceleration frictional forces applying here, but we're going to ignore that for the moment. Okay, so if we want to consider a streamline from point 1 to point 2, and we want to apply Bernoulli's equation here, we're going to first say, all right, if we're looking at point 1 to point 2, we're looking at a horizontal flow, we can ignore the z term. So gravitational forces are not playing a role in the way this fluid is moving. And I always get questions from students about when do we need to consider gravitational forces. And that's a tough call, especially when you're talking about biological systems where things are happening on the micro scale, and you're looking at very short distances, in an artery, and asking whether potential energy is really playing a role there. Like with everything in this class, it's a little bit of a order of magnitude approximation, whether that matters or not. Definitely when you've got something that's horizontal, like right off the bat, you know that you can pretty much ignore gravity here. So that's great. That gets rid of that z term. So we've eliminated that from our Bernoulli's. And we're left with a P1 plus 1/2 rho V2 equals P2 plus 1/2 rho V2, squared. All right, so we can rewrite this in terms of P2 if we want to know about what's going on the sort of post-stenosis side versus the pre-stenosis side. Now, I've mentioned before that we want to be able to say things in terms of cross-sectional area, average flow rates, all of these things. We can take advantage of our V1A1 equals V2A2 in order to fold that into what we've got here. And that becomes really handy because then you're essentially applying a conservation of mass to this problem. Okay? So you're saying essentially all the fluid that's passing at point 1 across that area there, that mass has to be accounted for at point 2. So if you're starting with a wide cross-sectional area and you're moving to something really tight, that velocity is going to increase. Intuitively, you know this. If you've got your garden hose and you want it to spray further, you put your thumb over it, right? And the velocity is increased. So that's what we're applying here, this conservation of mass. And that allows us then to use that information we might have about cross-sectional area to apply to the problem. So in this case, we have knowledge about reduction that's occurring due to the stenosis. So we don't have absolute numbers, but we have a ratio of A1 to A2 that we can use. We know things about what's happening pre-stenosis for our pressure and our velocity. We can solve for P2, and we can then also figure out what's going on with V2 based on this relationship. Okay, so we're going to apply just a simple, we've got a constant density here, so we're going to apply knowledge about the blood into the system. And then we're going to rewrite this P2 in terms of V1, V2, A1, and A2. Okay. So we weren't given enough to say that our V1, we weren't given enough to solve for our V1 and V2 here. Let me see here. Yeah, actually, I think he just didn't show it here. So if we've got V1, A1 equals V2, A2, and then we write V1, A1 over A, I'm sorry, my writing's so bad, A2 equals V2, then this should be substituted in for the numerator there, and you do then have all the information you need to solve. Okay, so then the P2 value is a value which, upon reflection, is not enough for the artery to collapse. So now this question about the issue of whether this is truly a frictionless system, to use the Bernoulli's equation. What Dr. Ethier mentions here, and I'm just going to have to erase this. Let's just get rid of all this. I've got to figure out how to use this system where it scrolls up with it. So I apologize. I'm getting rid of all this. What Dr. Ethier mentions in the lecture notes here is that you can actually calculate the Reynolds number. Have you learned about what the Reynolds number is? Yes? So it's really a balance. It's a way of describing your dominant physical properties for fluid flow and whether momentum is going to override friction or vice versa. So the Reynolds number is dependent on geometry. You have different characteristic lengths depending on if you're looking at a flat plate or you're looking at a round conduit. And then there are cutoff numbers or criteria numbers associated with the Reynolds number that says whether you're in a laminar regime or a turbulent regime. So what he's basically saying here is for a circular pipe, the cutoff number for turbulence is 2300. So if you actually calculate what the Reynolds number is in this situation, you come up with a value of 570, which says that you're in the laminar regime. Now, it turns out in the next unit, you'll learn about why it matters whether you're in laminar or turbulent for the purposes of this, these frictional forces, because you actually have more friction occurring at slow flow rates than you do at high flow rates. It's almost like you get enough speed going and you don't have to consider the roughness of that wall as much. But you'll see charts and things that really illustrate this more clearly. So we got a little bit ahead of ourselves in terms of what this question is asking for the interpretation of that lossless assumption. But that's where that's coming from. What I want to go into next is just a discussion of how we can use those Euler S and N relationships a little bit more to think about the way that a particle is moving depending on which streamline it's in. So if we consider this incompressible flow steadily in a pipe of a uniform diameter, and we want to neglect friction and assume a uniform entrance velocity profile and a uniform entrance pressure, and the question is the particle going to move faster if it's along the inner or the outer streamline? And it's specifically asking us to neglect gravitational effects. So let's look at this picture here. So what this problem statement is saying is that we've got some B1 here, which represents some kind of like average value. We've got a P1, and these are going to be uniform across this. So we're saying as we come in here, everything is going to be just a flat velocity profile and a flat pressure associated, or uniform pressure across there. And then it's asking, okay, we've got a curvature that's going downward, but we're going to ignore gravity for the moment. You can think of this as being something that's curving laterally if you want, and so you don't have to worry about the z direction. But for the purpose of the paper, we've rotated it so you can see what's going on. So you've got an inner and outer streamline that's taking place here. And then you're basically asking, if I'm a particle and I'm placed on a given streamline, am I going to land down here faster or slower than this guy, or vice versa? And we don't want to really consider the actual, like the advantage that a racer gets by getting the inside lane for a track meet or something like that. We're actually going to be considering the features of the velocity and the pressure to determine what's going on here. So if we think about the Euler N equation, that equation is talking about what's happening in the orthogonal direction, right? So we can consider at any point what's going on this way. And this gets back to this concept that we've been trying to kind of drive home in this class in terms of velocity profiles, and that at each point, if you move kind of laterally up there, you're looking in the orthogonal direction, you can have a different value taking place, which then is going to influence the overall behavior of what's going on. So in this case, at each point in the streamline, we can look at what's happening in that orthogonal direction and ask how that's influencing things. So this Euler N equation here is looking at the partial derivative with respect to that direction. So if you want to think about this in terms of your v sub x component, you're looking at what's happening in the y direction, right? That's the same kind of idea. Here we've got our pressure and our rho gz, and we're going to say that's related to our minus rho v squared over r. So the Euler equation was giving us something that basically takes into account a curvature through a radius in the denominator. It's taking into account a pressure. And then we said we're going to ignore this z term, right? So this can be actually eliminated. Now the key to thinking about this is that we've got a minus sign here. So we're left with a dp dn equaling minus rho v squared over r, which is saying that our dp dn is going to be less than 0. So what this says is that as we move across the streamlines from the inner to the outer wall, we're going to have an increase in our pressure. Okay, because P is usually considered P2 minus P1, the directionality of it. So in this case, if we have a negative, it's saying that we're going to have an increase from inner to outer. So if that's occurring, then we have to have a higher pressure outside than in. Yes?
Can you explain that one more time, why the pressure changes that direction?
Did I say it wrong?
No, I just wanted you to re-explain it.
Okay, so if we've got a minus dp dn here, we're saying that the dp dn term is negative. Then if we have, let's think about it this way, if we have high outer and low inner, then we're basically having let's think of it this way. I think I might have misspoken. If we have a tube and we have a P1 here and a P2 here, and we think of, I'm going haywire here. If we have a P1 here and P2 here, and we want to think about dP dx, we think about that being high to low, right? So P1, P2 is going to be high to low. So in this case, if we're going low to high, then we're going, just convention-wise, we're going negative, okay? So I think I might have misspoken the way I said that before. Okay. So then if we consider this dP dN to be negative, we're saying our outer pressure is higher than the inner pressure. So in terms of what that means, if we're applying our Bernoulli's equation between points 1 and point 2, and now we're using, essentially, the Bernoulli's is more in terms of the Euler-S equation, right? So now we think of our P1 and our P inner and our P outer, then we can have our P1 minus P out, P inner minus P out would be negative here, which means that our V1 is going to be greater than our V naught, or V out. Let's look at how this works. So if we've got a 1/2 rho V1 squared minus V2 squared equals P out minus P in. And we've already said that this has to be positive, right? Outer is greater than inner. Then that means that I keep doing 1 and 2. That's really misleading. It should be P out, P in minus P out. So our inner velocity is going to have to be greater than our outer velocity. Okay. So if that's taking place, then that fluid is going to travel fastest along that inner curvature, not because of there's a like slightly less distance traveled, but through this relationship here. Okay. So let's think about what that means. If you actually have particles that can move slightly different, and then either drive the pressure or vice versa, a difference in pressure driving the velocity, then this has an impact in the way you think about things like lift associated with airplane wing, or the fact that a race car hugs the road because it has that fin in the back, which is causing a pressure difference such that you're pushing down on the car. So you actually have geometries in which you're creating these airfoils that are going at different rates to cause pressure differentials, either in the positive direction or the negative direction, in order to have that occurring. So, as Dr. Ethier mentions, this is actually something that involves a lot more than the simplistic streamline and normal to the streamline relationship. And so if you have friends in aerospace engineering, they are looking at the hydrodynamics associated with, airplane wings and things like that would be influencing these different things. But for our purposes, we can think about this just in terms of this curvature and something basically happening faster on the inner versus the outer surface. Okay? So what we've wound up with, and I wish I could just get rid of, can I get rid of them? No, I can't get rid of them that way. Let's get rid of all this. There has to be a clear button somewhere on here.
You can probably open it up on the system viewer instead of Planet Explorer.
You mean if I download the PDF file
Yeah.
first? Okay. Thank you. I'll try that next class. So, let's scroll back up here. Okay, so if we go back to these two concepts here, we've got the N equation and the S equation. One is really relating what's happening sort of in the longitudinal direction that allows us to consider something that's being evaluated at one point versus another point longitudinally in the streamline. That was used to basically come up with our Bernoulli's equation that we use. The Euler inequation is something that you probably won't have to actually do much application of, other than understanding what we just went through in terms of what happens across those streamlines. But it's really useful to think about how you can have a pressure differential that's occurring due to this rolling curvature associated with something. So when we start with this S equation then, and we think about it in terms of a convention that makes more sense to us, then we can ignore just that S vector and that particle coordinate system that's moving along the streamline, and we can then just use our Eulerian relationships and think about, okay, if we're looking at something with a fixed viewpoint, and we're looking at what's coming in and coming out of our system, then we can evaluate what's occurring across this then with respect to our change in our z direction, our change in our height, and our change in our pressure and our change in the velocity. So what we didn't go through here is an example of that potential energy being changed. But you can have examples where that is really what's dominating in your system, that gravitational component. So oftentimes Bernoulli's is used for things where you've got something like, an example I always like, and this is used a lot in sort of 2210 type examples, is where you have a tank of water that's coming out a small conduit at the bottom. And so really what's driving that fluid flow out the bottom is that potential difference due to the size of the tank and really the weight of the water that's pressing down and causing that fluid to be pushed out the bottom. So that's an example of where that potential energy comes into play. Okay? So we do have a few minutes left. Should I open up the floor for questions about the MATLAB assignment? Given the caveats that I said up front, that I won't be giving explicit answers on how to solve it. Yes?
Can I ask a question about the exam? How much of problem set 4 is going to be covered on the exam?
That is a good question. I saw that in the Piazza post. And I'm not really sure how much of problem set 4 is being covered. I know that we're continuing with problem set 4 this week, such that I believe there's 2 more questions in the flip session and the recitation that are going to be covered. So that means that essentially most of problem set 4 is going to be responsible for on the exam. Yes?
I actually have a question related to the lecture. So for the problem with the stenosis,
Yes. Hey, guys, hold on. We're not done yet.
you got the final answer for P2 values of 27.6 millimeters of mercury, but then you say that this analysis predicts that it would collapse. How do you know what value would make it collapse and what value wouldn't?
That's a good question, because all they tell you is the pre-stenotic pressure and not what the pressure would be for collapsing. So I think in this example, I would say the fact that the pressure over here is so large and the fact that you have a low pressure elsewhere means that you don't have enough for collapsing. But I don't know if there is a certain threshold that, under these conditions that people look for artery collapse. It's really an application of real world numbers without the background associated with it to give you an idea of what's an appropriate threshold for that. But my interpretation is that they're looking to see, do you have a larger pressure or a smaller pressure at that point that would predict something, pushing down and collapsing the wall.
So if this is a problem, how would we go about analyzing it? Would we be expected to just give a numerical answer, or would we expect to go into detail about this would predict this one?
I think it depends on the way a question is written on the test. Every once in a while when I write a test question, I'll ask for an extra component that may be worth 5 points that asks for some physical interpretation of that, like, is this large enough to cause a difference or not, that kind of thing. But unless you're specifically asked, then you're only supposed to give a numerical or symbolic answer. Other questions? Okay, I will be holding office hours Wednesday at 3 o'clock for any last-minute panic questions on the MATLAB assignment before it's due at 5. Oh, I'm sorry, 11. I'm sorry.
On Wednesday.
On Wednesday, yeah.